In today's video, I would like to introduce a very nice problem of Germany Mathematical Olympiad, the year 1996-97. Here is the following question. Determine all primes p such that x, y as integer numbers, x, y are solutions of this equation system. So the left hand side of this equation system is involving p as a prime. The right hand side of this equation is involving x and y as variables. In fact, this is very nice and interesting problem to work on. If you would like to give it a try to this problem prior getting to the solution, just go ahead and pause this video when you come back to see the full solution. So by the way, don't forget to support us with your like and subscribe. Now let's go ahead and jump into the solution. As you know, the prime numbers, it could be even prime or odd prime. So we are going to check if p is even prime. If p is even, this means p equals 2. I'm going to insert number 2 into this equation to see what's given us. So we'll get here 2 plus 1, which is 3. We'll get 2 plus 1 equals 3 equals 2 x squared. X as an integer number, that means x squared equals 3 over 2, which is impossible. Okay, that means p is an odd prime. This one is telling us p is super equal to 3 as an odd prime. The second thing, we are going to make the comparison between x, y and p. First table, I'm going to compare x and y. 2 is multiplied by x squared equals p plus 1, and 2y squared equals p squared plus 1. It's clearly x is strictly inferior than y, okay, based on these two equations. Now I'm going to compare y and p. This is very clear here. Y is strictly inferior than p, because let's take y equals 5 as an example. If you take in the 5 here, is given as 25. 25 is multiplied by 2, which is 50. So we'll have p squared plus 1 equals 50. That means p squared equals 50 minus 1, which is 49. So that means p equals 7. So p equals 7, equivalent to y equals 5. That means p is always bigger than y. Okay? So this one is telling us y is strictly inferior than p. This is the second thing. The third thing, we are going to prove p not divide to x squared and p not divide to y squared. Okay, this is the main goal. We are going to prove this one. So by the way of contradiction, we are going to assume p divides to x squared and to see what's given us. So by the way of contradiction, suppose p divides to x squared. P divides to x squared is equivalent, according to the divisibility statement, we will have 2x squared equals p is multiplied by k, where is k is a sum of natural numbers. Okay, now I'm going to take this value and insert it into this equation. So we'll get p plus 1 equals pk. So by taking p to the right hand side of this equation, I will get here pk minus p, which equals p factor k minus 1 equals number 1. So in the other words, p equals 1 over k minus 1. So since p is an integer number, so that means the only case we have k minus 1 divides number 1, we have to give k equals 2. Because k equals 2, that means 2 minus 1, which is 1. But the problem, but p is an odd prime, which is p must be superior or equal to 3. That means this is contradiction. What does mean? This one is telling us p not divide to x squared, because our assumption was wrong because of this contradiction. That means p not divide to x squared. So I'm going to check with the 2y squared. So the same thing, by the way of contradiction, suppose p divides to y squared, equivalent according to the divisibility statement. So I have 2y squared equals k prime, for example, k prime p. So I'm going to do the same thing by taking this value and insert it into the second equation to see what's given us. So we'll have p squared plus number 1 equals k prime p. So I'm going to take this k prime p to the left hand side of this equation, and at the same time I'm going to take the p as a common factor. We'll have p factor p minus k prime equals, also I'm going to take this number 1 to the right hand side of this equation. We'll get minus 1. This is impossible. This is contradiction. This is impossible to have this product equal to minus 1. Okay, this one is telling us p not divide to y square. Okay, now we have proven these two cases. Now let's move on to the next case. Previously we have proven all these things: p not divide to x square, p not divide to y square. So this equivalent p not divide to x square equivalent, according to the divisibility statement, to x square is congruent to 1 mod p. The same thing with the next one, p not divide to y square, according to the divisibility statement, I will have 2y square is congruent to 1 mod p. This one is telling us I'm going to take 1 to the left hand side. I will get 2x square minus 1 is congruent to 0 mod p. The same thing here, I'm going to take 1 to the left. I will get 2y square minus 1 is congruent to 0 mod p. So both statements are indicating p divides to this term, p divides this term, and p divides this term. So the next thing that I'm going to do now, I'm going to subtract this equation from this equation. So I will have 2x square minus 2y square. This minus 1 will be cancelled out, is congruent to 0 mod p. Okay, then I'm going to, since this one is written on the form of the two different of the two squares after taking 2 as a common multiplier, so we'll get, I'm going to factor this one out. I will get 2 is multiplied by x minus y, factor x plus y is congruent to 0 mod p. Now p will divide this one or divide this one, since p not divides 2 because they are different primes. Okay, so 2 is an even prime, p is an odd prime. So I will have one of those, p divides this one or p divides this one. So that's mean I will have x minus y is congruent to 0 mod p, or x plus y is congruent to 0 mod p. This one, according to the divisibility definition, I will have x minus y equals k is multiplied by p, whereas k is a sum of natural numbers, and also x plus y equals k prime is multiplied by p, whereas k prime is a sum of natural numbers. Okay, now we have a choice, which one is a right, which one is not a right. So if you take a look carefully at this inequality, we have x minus y is strictly inferior than 0. Okay, this one is strictly inferior than 0. This is, but k is multiplied by p is strictly superior than 0. Okay, because this one is positive, this one is negative. That means this one is no. Okay, not taking this one. This one is yes. So I'm taking this one as a right choice. The next step, we are going to calculate the value of k prime. So okay, because now we don't know the k prime, what's the number of k prime. So to do that, I'm going to use this fact. So I have x strictly inferior than p by adding y on both sides. I will get here x plus y is strictly inferior than p plus y. So x plus y will be replaced with this one, equivalent with k prime p is strictly inferior than p plus y. Okay, now I'm going to move over p to the left hand side. I will get here p factor k prime minus 1 is strictly inferior than y, and also y is strictly inferior than p. So now I'm going to cancel out p from both sides. I will get k prime minus 1 is strictly inferior than 1. Okay, after simplification, because this one, after you taking off p from both sides, this one is turned 1 here. Okay, now by taking minus 1 to the right hand side of this inequality, I will get k prime is strictly inferior than 1 plus 1, which is 2. This one is telling us since k prime is a positive integer, that means k prime must be equal to 1. Now I determine the value of k prime. I'm going to take this fact and insert it into the original equation. So I will have x plus y equals p. I'm going to calculate the difference of these two equations. I'm going to put p squared plus 1 minus this one. So I will have also p squared plus 1 minus p minus 1, which is 1, equals 2y squared minus 2x squared. Okay? This number 1 will be cancelled out. One is positive, the other one is negative. I'm going to take p as a common factor here. I will get p factor p minus 1. This one is on the form of the difference of two squares. I will get 2 factor y minus x is multiplied by y plus x. Then I'm simply going to insert x plus y with p and y minus x in terms of p and. So here for y minus x, I'm going to add minus 2x on both sides. I will get y minus x equals p minus 2x. I will get 2 is multiplied by p minus 2x. For y plus x, it will be replaced with p. Okay? Now I'm going to cancel out one of the p from the left and the right. I will get here p minus 1 equals 2. By distributing this one out, I will get 2p minus 4x. So by taking minus 4x to the left, I will get 4x minus 1 equals 2p minus p, which is p. Since I found p, also we have p plus 1 equals 2x squared. That means p equals 2x squared minus 1. So we'll have here 2x squared minus 1. Then I'm going to cancel out minus 1 from the left and the right. I will get here, by moving 4x to the right, I will get 2x squared minus 4x equals 0. In the other word, I'm going to take 2x as a common factor. I will get 2x factor x minus 2 equals 0. Okay? I have ended with this expression. I will have two solutions here. I will have x equals 0 or x equals 2. X equals 0 doesn't work because x, if you replace x with 0 here, you get p plus 1 equals 0, which is impossible. X will be replaced with number 2 here. Now I'm going to take this little space here. By plugging number 2 into the original equation, I will get here 2. I will get 2 square, which is 4. 4 is multiplied by 2, which is 8. So we'll get p plus 1 equals 2 is multiplied by 2 square. Okay? So we'll get p plus 1 equals 4 is multiplied by 2, which is 8. That means p equals 8 minus 1, which is 7. Now I found the value of p, which equals 7. This is the only solution that we found, p equals 7 as a prime. I have done this problem. If you are interested in watching this one, don't forget to support us with your like and subscribe. Thank you for watching. I will see you next video. Bye.